In this question, you can see that there is a composite bar which is made up of two bars of same material and same length L, but the area of cross section of OB is twice as that of OA. Okay, and this composite bar is kept on a frictionless surface, and we are increasing the temperature, and we have increased the temperature by delta theta. So we have to find out the x coordinate of the joint if the coefficient of linear expansion of material is alpha, and it is also given that this is origin. Okay, so we have to find out the new x coordinate of the joint. So we know that as area of cross section of this rod is twice as compared to this one, therefore the mass of this rod will be 2m. And let us assume that this is origin, so the center of mass will remain at its position, and the center of mass x would be equal to xcom would be equal to 2m into LOB by 2 plus, in fact, minus m into LAO by 2 and divided by 3m. Okay, so this is the xcom. So delta xcom, which is the change in the position of center of mass, will be equal to this is m into delta LOB minus m into delta LAO by 2 divided by 3m. Okay, so you can see that this is the change in length. So you can write it down as delta LOB minus delta LAO by 2 divided by 3. Now delta xcom is equal to delta LOAB. So the change in length of this rod will be L and alpha delta theta, and the change in length of this second rod would be same, minus L alpha delta theta. So you can see that this is L alpha delta theta by 6, but we know that the net external force acting on the system is 0. So F external is 0. So center of mass will not shift. So if center of mass is not shifting from the original position, then we can say that this shift is the shift in the coordinate system. Okay, so this coordinate system has shifted in the backward direction. So we can say this joint has shifted in the backward direction. So shift of joint will be equal to minus L alpha delta theta by 6. Okay, so now we move on the next question. In this question, you can see that there is a rough inclined plane whose coefficient of friction is 1 and its inclination is 37 degree. There is a rod of mass m and length L which is lying on this inclined plane, and we are increasing the temperature of this rod. Now on increasing the temperature of this rod, we see that there is a point P on this rod which does not move. So we have to find out the distance of that point P from lower end A. So let us suppose that there is a point P here which is not moving. Now the fact that this point is not moving is the net force acting on this rod in the upward direction, and the net force acting on this rod in the downward direction is same. So what we can do, we can just see that when this rod will move in the upward direction, a force on this rod will be acting in the upward direction. Let us name that force as F top. And when this rod will be moving in the downward direction, a net force acting on this rod will be F bottom. So we can say that if the mass of this part is m1 and the mass of this part is m2, and we can say that when the rod will expand, this part will move in the upward direction, so the friction will be acting on this part in the downward direction, and this is F1, and m1g sine theta will be acting in the downward direction on this part. And when this part is moving, then m1g m2g sine theta will be acting in the downward direction, while friction will be acting in the upward direction. Okay, so net force is 0 because these parts are moving very slowly. So F on bottom will be equal to this is F bottom plus m2g sine theta is equal to F2. So F bottom will be equal to F2 minus m2g sine theta, and F top will be equal to F1 plus m1g sine theta. So F top and F bottom will be same, so we can equate these two. So we can see that F1 plus m1g sine theta, F1 plus m1g sine theta is equal to F2 minus m2g sine theta. Okay, and m1g plus m2g, or we can say m1 plus m2 g sine theta is equal to F2 minus F1. So this is m, so mg sine theta is equal to F2 minus F1. Now mg sine theta is equal to F2 is the friction acting on the lower part. So let us suppose that the length of the lower part is x and the length of the upper remaining part is L minus x. So the friction acting on the lower part will be x into m by L into g into mu cos theta minus friction acting on the upper part, this part would be L minus x into m by L into g into mu cos theta. We know that mu is 1, and cancelling mg with mg, mu is 1. So sine theta is equal to x, this is L, so sine theta is equal to x cos theta minus L cos theta plus x cos theta. Okay, so L sine theta plus cos theta divided by 2 cos theta is equal to x, and x will be equal to L by 2 tan theta plus 1. Okay, so x will be equal to L by 2, tan theta is 3 by 4 plus 1. So x will be equal to, this is 7L by 8. This is the position of that point from the bottom where that would not move when the rod will expand. Now in the B part of this question, this rod is contracting as temperature is falling. So once again there would be a point Q which would not move, so we have to find out the distance of that Q point from the bottom point A. So let us draw the diagram again. Let us see that this is the rod and there is a point Q, and this rod is contracting, so it would be moving in the upward direction and this would be moving in the downward direction. So if I draw the diagram of this rod, so you can see so that there would be a pulling force acting on this rod, let us suppose F bottom, and this friction will be acting in the downward direction, as well as m1g sine theta would be acting in the downward direction. For this part, we can say that there would be a pulling force acting on the downward direction, F top, and friction would be acting in the upward direction, F2, and mg sine theta, m2g sine theta will be acting in the downward direction. So F bottom from this diagram will be F1 plus m1g sine theta, and F top from this diagram will be equal to F2 minus m2g sine theta. Again, these forces will be equal, so F2 minus m2g sine theta will be equal to F1 plus m1g sine theta. So F2 minus F1 will be equal to m1 plus m2g sine theta. Okay, and now we can say that F2 minus F1. So F2 is this part, F2 is the friction acting on this part, on the upper part. So length of this part will be L minus X. So we can say that L minus X and minus X is the length of the bottom part, this part, into M by L into mu into G into cos theta. This is the net friction. And M1 plus M2G sine theta will be mg sine theta. Cancelling mg with mg, and the value of mu is 1. So L minus 2x by L, mu is 1, will be equal to tan theta. 1 minus 2x by L is equal to tan theta, which is 3 by 4. So 2x by L is equal to 1 by 4, and x is equal to L by 8. So the distance of that point from the bottom will be L by 8, which would not move when the rod will contract. In this question, you can see that there is a rectangular tank that contains water up to height h, and there is a metal rod that is hinged to the bottom of the tank so that it can rotate freely in the vertical plane. Now the total length of the rod is L, and it remains at rest with some part of it lying above the water and some part below the water. So in this position, rod is making an angle theta with the vertical, and we are assuming that y is equal to cos theta. So we have to find out that fractional change in value of y when the temperature of the system increases by a small factor delta T. And it is given that the coefficient of linear expansion of the material of rod and tank is alpha 1 and alpha 2, and the coefficient of volumetric expansion of the water is gamma. Okay, now let us see that I've already drawn the diagram of buoyancy and mg. Now buoyancy will be equal to L immersed into cross section of this rod is, let's suppose we are assuming that the cross section of the rod is A, and this is A, and into this density of liquid, which is water, rho W into G, and the value of mg will be equal to L total into A into rho of rod into G. Okay, so this is the mg and buoyancy. Now we are balancing the torque about hinge to be 0. So we can see that this length will be equal to L immersed by 2 sine theta, and this length will be equal to L by 2 sine theta. So what we can say that torque of mg will be mg into L by 2 sine theta, and it would be balancing the torque of buoyancy, which would be L emerged or buoyancy into A into rho W. In fact, let us write down the buoyancy into L emerged by 2 sine theta. Cancelling out the sine theta with sine theta, 2 with 2. So we can see that mg, we can replace the value of mg, which is LA rho of rod into G. So this is L into A, this is L square because here is also a L. So mg is equal to mgl is equal to L square A rho r G, and buoyancy will be equal to Li square A rho W into G. Cancelling G with G, you can see that this is cancelling A with A also. So L square rho rod is equal to Li square into rho water. Now we can say that L emerged will be equal to H sec theta, because L emerged cos theta is equal to H. So L emerged is H sec theta. So L square rho rod is equal to H square sec square theta into rho water. Okay, so now we have to find out cos theta. So cos square theta is equal to rho water H square divided by rho rod L square, and this is cos theta, so this would be, there would be a root, and this is y. Okay, so y is equal to rho water H square by rho r L square to the power half. Now let us suppose that z is equal to rho w H square by rho r L square. So dz by z will be equal to del rho w by rho w plus del rho r by rho r, and plus that 2 h delta h by 2 delta h by h, and plus 2 delta L by L, and there would be a negative sign for these one because they are in the denominator, so here would be a negative sign and also there would be a negative sign here. Okay, so this is dz by z, and y is equal to z to the power half, so dy by y will be equal to 1 by 2 dz by z. So it would be 1 by 2 del d of rho w by rho w minus d of rho r by rho r plus 2 dh by h minus 2 dl by l. Okay, so now we can also write down that h is equal to volume of liquid upon area of the container. So dh by h will be equal to del v by v dv by v and minus dA by A. Okay, so we can write it down like that. So dy by y will be equal to 1 by 2. This is d rho w by rho w and minus d of rho solid, rho of rod by rho of rod, plus 2 dv by v minus dA by A, and minus 2 dl by L. So this is half. Now rho water, we know that the value of rho water is equal to the expansion coefficient of water is gamma. So rho water by rho water will be equal to minus of gamma dt, and d of rod by original of rod will be minus of, so there would be plus, and 3 times the coefficient of linear expansion of rod is alpha 1, so 3 alpha 1 dt plus, this is volume of water, so it would be twice of dv by v would be twice of gamma dt, and minus twice of area of the rod, so area of the rod will be equal to dA by A would be equal to 2 alpha dt, and this is minus 2, L is total length of the rod, so minus 2 alpha dt. So it is half. You can take dt common, and you can see that this is 2 gamma minus gamma, which is gamma, and the expansion coefficient of the container is alpha 2, so when we are writing dA by A, we have to take alpha 2. Okay, so this is alpha 2 and L is the length of the rod, so this is alpha 1. So you can see that this is 3 alpha 1 and 2 alpha 1 with a negative sign, so it would be plus alpha 1, and here it would be minus 4 alpha 2, minus 4 alpha 2. So this would be the fractional change in y. Okay, now in the next part it is given that what is the necessary condition for theta to increase. So we know that if theta increases, cos theta will decrease, and cos theta will decrease, then dy would be negative, and dy to be negative, it is necessary that 4 alpha 2 should be greater than gamma plus alpha 1. So this is the condition for the B part in which theta will increase. Thank you.